some of these things that I also noticed that were just common mistakes, right? That we are making kind of across. I saw students making across everyone that I looked at. And it still applies to the kind of things that we're talking about today. Okay. So all that being said, where do we kind of leave off? So we were talking about measurement error that existed. And last class, primarily, we only looked at when it existed in the independent X right-hand side variables, right? We said, which type of these did we not have to worry about in terms of we could actually put a sign to what that bias would be. Classical or complete, if you want to think about this word classical, it just means completely random, not correlated with that X variable at all. When it's completely random or classical measurement error, we said we have a bias that is going to push our estimate closer to what value? I'm going to make it smaller, pushing it closer to 0. If it pushes it closer to 0, right, we call that attenuation bias. But if the estimate is getting closer to 0, what is our test statistic also getting closer to? So our test statistic is that coefficient estimate over that standard error. So if it's pushing our test statistic down, it's also pushing our test statistic down, which is doing what to our p-value? So I've got my test statistic. This is where this isn't like a cumulative exam on the final, but we're kind of comprehensive building on what we've talked about. If my test statistic is lower, the area to the right of it, which is my p-value, is going up, which makes it less likely I can reject the null. It's pushing it closer to 0, which is what I assume, that's what the null is, that I assume this coefficient is equal to 0. Right? So when we have classical measurement error in the independent variable, we're less likely to find, we're going to find a coefficient that's a smaller size, but also of lower statistical significance. Now, when we have non-classical measurement error, all bets are off, right? The bias could go in either direction. If it pushes the coefficient estimate higher, what's going to happen to our test statistic? It's going to be even larger. P-value is going to be smaller. We might even be more likely to reject in that case, right? So it's going to influence not only the size of our coefficient, but the statistical significance, right? So we don't like this non-classical measurement error. So today, we'll now kind of flip things a little bit and say, what happens if we have measurement error in the dependent or the Y variable? Right? So if I have measurement error not in my X variable, my Y variable now, I can think of the actual value I see in the data is Y tilde. Right? That's the reported value I see. The actual value is Y. Okay? So we can go through a similar thought experiment that we did last class. I'll go through it relatively quickly because you're not going to have to reproduce this. But the idea is I could then rewrite the Y variable I'm seeing, or Y tilde, is whatever the actual Y is, plus this new measurement error. Now, what ends up being true if the measurement error is in my dependent variable, that measurement error would exist, right, when calculating the actual Y value. So it's going to show up kind of here on both sides. Now, when we look at the actual statistics, that measurement error on the right-hand side kind of gets wrapped up into just our normal error term. Okay? So if I then think about rewriting this, when I'm running these regressions with the self-reported data that might have data measurement error in it, my error term is going to include whatever the true error term is plus that measurement error. Okay? So I then kind of have to think about, I can rewrite my composite error term as the original measurement error the original error that existed plus the measurement error. So what's now going to be true? Well, what was one assumption that we needed? The expected value of our error term, given these different values for X, needs to be equal to 0. Now, expected value of that composite error now, where U is the error plus our kind of measurement error. We now need that expected value to be equal to 0. So we'll start to think through two scenarios, right? Will the, if our assumption is correct before, that regular error, the old error term, should still have an expected value with X of equal to 0. But will the measurement error, right, that we've now introduced, will it have an expected value of 0 given different values for X? Well, if we have statistically significant results, X should be correlated with Y, right? It's likely that that's not going to be the case. right? If we actually are including control variables that matter, now the expected value of our measurement error might not be equal to 0 for different values of x. Okay? So we're going to have two kind of scenarios, right? So will this estimate we see be an unbiased estimator? Well, let me think about this, right? Here we go. So if this was what we would call classical measurement error, that it's just random. When people were reporting these values, it didn't depend on X or Y. It was just completely random or classical measurement error. Well, then that measurement error shouldn't be correlated with those X values at all. So what's going to happen to our estimate? Our composite error, that U I was writing, well, if the expected value of one component of it for the X values is 0, and the expected value of the other component of it was equal to 0, I won't have any issues, right? So if I have completely classical measurement error in my dependent variable, or it's completely random, I still have an unbiased estimator. I don't have to worry about it, right? Which is good news for us, right? So like if I'm trying to predict things like, I think I used examples last class, like maybe I'm trying to predict alcohol use. And I know that people are going to, but if they're only misreporting because they can't remember like who counts how many drinks of alcohol they have every single week, if it's completely random, our coefficient estimator shouldn't be impacted, at all. Now, if different values of this X variable impact the size of that measurement error. So I think I had here an example. Yeah, thought this one. So let's say I'm trying to predict drug use, and I've got whether or not they were a police officer, right? And I've got maybe a bunch of different controls as well. Excuse me. If it's self-reported drug use, then the value I actually see will contain measurement error, right? So I'm going to see like this self-reported drug use. So I now need to think about, okay, is the expected value of that measurement error that I see in my Y variable, is that going to be correlated at all, or will the expected value of it for different values of X now, whether or not they're a police officer, will that still be equal to 0? So I think through this example, compared to like, let's say, I don't know, someone is running surveys and they just ask people at random what their drug use is. I mean, probably most people underreport it, but that's okay as long as everybody underreports it. But if I don't think this data is ever going to be accessed by anyone, do I really care if this random person taking these surveys knows what my self-reported drug use is? No. So my self-reporting might be pretty accurate. If I'm a police officer, I might be a little bit more concerned that someone now sees that I reported I actually use drugs, right? And so because different values, this is a simple example where I've got a dummy variable, right? So when I'm looking at non-police officers, they're not really concerned with if this data exists out there because it's probably not going to cost them their job, right? You ask any Fortune 500 company, they probably expect that many of their employees are using drugs, whether that's amphetamines or whatever it is, right? Now, if I think that I might lose my job as a police officer, I'm going to be way more likely to vastly underreport my drug use. So now the expected value of the measurement error, given different values of this dummy variable, I now expect that when this is equal to 1, my measurement error is going to be much larger. So the expected value would change depending on the value of that X variable. So if it's not equal to 0, that violates our assumption because we are now thinking about the expected value of that composite error, which includes the original error we've kind of always had in our regressions, but then also plus that measurement error. We need this to be equal to 0, so we need both of these to be essentially, you could think of this almost as uncorrelated with that X variable. If they're not, now our regression results will be biased. And in which direction, it's a little bit harder to think about, but it could go up, it could go down. All right? I won't ask you necessarily to tell me whether it goes up or down. We just know that it's going to change. It's going to be it's no longer going to be unbiased, it's now going to be a bias estimator. So that's kind of the setup example that we're thinking about, right? So kind of a similar story as measurement error in the independent variable. We said when it was in the independent X variable, classical measurement error, we could at least say that the bias, it was going to push it towards 0. Non-classical or non-random error, it could go up, it could go down. We don't know. In the dependent variable, classical measurement error was going to cause our estimates to be exactly the same. It's a good thing, right? If it's non-classical, could go up, could go down, we can't say, right? Without knowing more about that relationship of that self-reported variable and our X control variable that we were looking at. Right? I tried to choose an example here that I think makes sense. You could think about maybe what's another one. I always think about this, even if I was trying to predict, I don't know, let's say hours studied or something like that in terms of the time put in towards a class. It's likely that if I had self-reported values, students who, if I have as a control variable on the right-hand side, GPA, right, prior to the semester, it's likely that for different values of prior GPA, people with higher GPAs are likely going to maybe over-report how many hours they studied by a small amount. The students with lower GPAs tend to self-report values that are much larger. And so there, my measurement error would depend on control of prior GPA I was looking at. So we've got all, we can think of tons of different examples here. I'm just trying to give something to kind of solidify this idea. So let's take a look at what this looks like in Stata, because part of this class is its application of statistics. And sometimes I think seeing it proving something to yourself with data will sink in a little bit more. So let's go to that data issues file, and we left off right here. And say I put a note in there so I remembered, right? So we're looking at measurement error in that dependent variable. So I'm now going to I think we were looking at this last class, but this relationship between GDP and BMI, just so we kind of keep using the same example. I'm now going to create a variable, right? And actually, I guess I have to open the file up first, right? That would help. So I open this file up, I come down here, and I'm going to create, just so we're all working with the same numbers, I'll copy and paste this just so we're picking up where we left off. So I open that file up. I'm going to set the seed so we get all the same random numbers, right? Just so that we're working over the same values if you're working along. And I'm going to create this measurement error, which is uniform from -1 to 1, right? So it's completely random, right? Somewhere in this range. And I'm then going to create this GDP that includes that random measurement error. So we should have classical measurement error. It's completely random. So when I create this new GDP measurement error variable, when I run these two regressions, one with the actual GDP and one where I have the measurement error that was classical, what should be true about the coefficients? We said if it's classical measurement error in the dependent variable, it should be the same. Should be the same. So hopefully, okay. Oh, I forgot to do something else to make these numbers easier to look at in class. What did we do last class? I'll kind of copy this down here. I'm going to scale this variable so the numbers are a little bit prettier, easier to look at. So I'm just going to go scale that. Actually, I'll rerun all this code. So we're going to open that file up. If you didn't want to copy and paste it yourself, we'll scale that GDP variable, set the seed, create the measurement error, and then we'll kind of come down here. That's what I copy and pasted here, just so we're kind of, if you're going back to looking at it, you could kind of start where we started in class 2. So now when I create this GDP measurement error variable and run these two regressions, what should I see? Sure enough, I get the exact same coefficient, right? So not only do I get the exact same coefficient, what's true about my statistical significance? What would I be looking at? Here's where I'm getting sometimes on these problem sets, I'm being pretty lenient in the way I would grade something like this. But even though I see the p-value is 0 for both of them, that's only to the third decimal. What tells me that these are actually the exact same p-value? I'm seeing the same test statistic as well. Let's assume just for a second, thinking about just not this material, but other material, if that second regression had a test statistic of 4, the p-value will still display and look like it's 0. But which one of those would actually have less statistical significance? Even though the p-value looks the same, it'd be the one that has a slightly smaller test statistic. So when I'm thinking about statistical significance, my stata output, I can use these commands that I really haven't used a lot in this class, although some people, maybe they put in some work outside of class, maybe an AI generated it for them, but you can grab the actual p-value, right, from this regression and compare it out to whatever decimal you want to, right? But we don't need to do that if we can see that there is a difference in the test statistic. Whichever has a smaller test statistic would always have a larger p-value or less statistical significance. Here, exact same p-value, or sorry, exact same test statistic, so exact same p-value, right? So good. Classical measurement error, we don't have to worry too much about it, okay? And you could rerun this and do it for like a normal distribution. As long as it's completely random, won't change your estimate. Okay? So this is good when we're wanting to look at trying to predict self-reported behaviors if it's our dependent variable. Now, it's not good news if instead, and this is a very extreme case, but let's say as GDP is higher, okay, it's less likely we're getting really precise estimates of it. So you can kind of imagine for lower countries with lower GDPs, you know, maybe if I have a GDP, it's a couple billion, maybe I'm off by a couple million. It's a pretty small error, really, when you think about it. But if I'm talking about GDPs in the trillions, I could be off by a couple billion. It still isn't a very large percentage. So the actual size of that measurement error could depend on the level of GDP, right? Or it could depend on, in this case, right? So I have it kind of depending on GDP. So I'll kind of rerun this, right? And what I end up seeing is if I create this new GDP that includes measurement error, where the measurement error is a function of that Y variable, I now end up with, right? It's not non-classical now. I end up with a wildly different coefficient. Okay? Now, I can't say whether it's going to go up or down. That kind of depends on the relationship of that measurement error to whatever that X or Y value, whatever that Y value was here for we were looking at, which was GDP. So non-classical measurement error is going to be an issue because we really can't say what's going to happen to the coefficient. Okay? Classical measurement error, we're perfectly okay with that. That's actually like of all the measurement error we've talked about, that's the best case scenario, right? Because it won't change our estimates. Any questions on this IoT? Kind of push it one step further here. So I'm going to copy this, paste it. I'm going to create a third measurement error where it's now not going to depend on the Y variable, but this is more of what we kind of talked about in the slides. It's now going to depend on that X variable. So now the expected value of what that measurement error is, I mean, here I've kind of made it, I've multiplied, make it an actual function of that X variable. So once again, if I create this and run my regression, I don't see 60,088. I see something that's almost zero, right? I have no idea. And in fact, now it's highly statistically insignificant. So when I have measurement error that depends on the X values, those control variables I use, in this case, I just used one, which was BMI, I might see a coefficient that, you know, the actual coefficient we knew was 60,088, I think it was. Now we've almost got a coefficient estimate of zero. So we might not find an effect if we have measurement error that depends on those X variables, when in fact, we didn't have the measurement error. There's a highly statistical significant relationship between BMI and GDP. Okay. So that's, I don't know, kind of just a way to prove with data, creating the actual measurement error yourself. Now, we don't have the luxury of this in the real world, right? The measurement error is usually it's self-reported data. We don't really know exactly what its relationship is with those control variables we've included. But if we think that in any way that the measurement error in our self-reported dependent Y variable is influenced at all by any of our controls, we know we're going to have bias estimate. We don't have a solution yet. That'll kind of be next week. Okay. Any questions on anything there before we kind of jump back into the slides and keep moving? Okay. So I now have a little bit more of a fun example. We can start to think about. This isn't really measurement error, but it's going to be it'll kind of be measurement error, and it'll kind of be what we talk about next, which is like we have missing data. Okay? So I'll use this example, and hopefully we can have a kind of good jumping off point, because I think I've used this in like lower level stats courses. Hopefully you haven't seen this example before. Nobody had me for 370 this summer, did they? That good. All right, so, right, let's go all the way back to 1936, right? There's this academic paper that somehow found like all this data on the presidential election, right? So 1936, we had Alf Landon, which I had no idea was a presidential candidate until reading this paper. What a great name, right? So they sent out this survey. Now, what ended up happening is they sent 10 million out, but they only got 2.5 million surveys back. Okay? So we know the population. Let's just assume it was the 10 million people they sent it to. Our sample was only about a fourth of that. So we got a smaller sample than the population. And it predicted that it was a landslide victory, 57% of the popular vote, almost, huge swing in the electoral vote. But it predicted that Alf Landon was going to win. We know he didn't, right? So what went wrong? Why was their data incorrect, right? When you think about two different scenarios that could have happened here. So we have two different types of bias that can be built in when we're putting out survey data, or we're collecting data. The first can be our selection bias. If I sent out 10 million, and I believe Alf Landon was the Republican candidate. So if I sent out 10 million random surveys, and let's say I tried to do my best, I sent 5 million to registered Republicans, 5 million to registered Democrats. If the 2.5 million I got back, for whatever reason, only the Republicans responded, 0 Democrats did, well, then my sample is going to be biased towards the Republican candidate, right? I would have to have that an equal amount of both registered Democrats and Republicans sent these surveys back. I'm using the extreme to kind of paint that if no Democrats sent it back, but only Republicans did, well, then of course my results are going to predict that Alf Landon, the Republican candidate, is going to win, right? So that's my idea of a selection bias, right? That I have some systematic underrepresentation of a certain group. Now, my non-response bias, sorry, I talked about these already out of order. That's my non-response bias, right? That I wasn't getting a response from Democrats. Now, let's assume instead of sending 5 million surveys out to each group, for whatever reason, my selection process, maybe people that were reading the Literary Digest, right, were older and tended to lean a little bit more towards the Republican candidate, right? That's something I would say we could put in today's context as well, right? Typically, as you're older, we see people vote more likely to vote for that Republican candidate. Well, then when I sent these 10 million surveys cards out, maybe I wasn't sending 5 million to registered Republicans and Democrats. Maybe I was sending like 7 million to registered Republicans and 3 million to registered Democrats. So even if everybody responded, I'm going to have a selection bias in that my procedure to send out these surveys was over selecting from that Republican group, right? Now, the non-response bias, that was the first one I suggested, where if I just didn't get as many back from the Democratic people that I sent it to. So both of them likely exist at the same time. And in this example, both of them likely would cause me to end up with more registered Republicans in my database. So my estimates are not going to be reflective of the entire population when I have these bias exist, right? In fact, they kind of went through. So I think to kind of sell this a little bit more, another thing that they actually did in my example, I didn't state yet, but the way they got these names was not actually people that read the Literary Digest. Grandparents used to always have this in their home, by the way. This was like a Bible to old people, right? But the way they found these names, right? They didn't just send them to like people who were subscribed to this little magazine. They looked at car and telephone registrations, listed them, right? The only way that you ended up in this database was if they had a car registration and a telephone line to your home where they could verify like this is a person that actually exists. They then sent it to that mailing address. Who owned cars and telephones or had their own telephone line in 1936? People who are really wealthy, right? So right away, I have what type of bias? I'm going to be over selecting from a group that I know is wealthier individuals, not case for any one person, but on average, income is positively correlated with voting for the Republican candidate. Typically, it's because they protect rich people's money a little bit more. I'm not breaking any news, I don't think. So if we only end up with kind of wealthy earners, we have this over selection or a selection bias where we're going to end up with more Republican voting individuals in this database, right? So we've got that selection bias. Now, the non-response bias, there's no reason to believe that, I don't know, registered Republicans are any more likely to respond to just a random poll. So I shouldn't ahead of time think that there's going to be a non-response bias. I would expect both groups would respond equally. Well, they actually were able to identify a lot, like the original people the surveys were sent to, and reached out again to them. And I forget what year this was. It might have been like in the 70s. And then I found a lot of them and said, did you actually respond to this poll back in 1936? Okay. So we can actually see who responded. So they found that for people who owned a car and telephone, right? Here, this is kind of our selection bias, right? People who owned a car and telephone actually ended up voting more for Landon. So the prediction of our poll would have been correct, right? But that's because our sample only selected off of people in this group. When they actually went back and asked these people, who did you actually vote for? And they looked at people who only owned a car or people that only owned a telephone. So first of all, back in 36, if you had a telephone, you were likely living in a large city that didn't have power, telephone lines ran out to like rural areas. And so these are probably going to be people living in cities, right? Or people who are just kind of owning a car only. What's weird is that for both those groups, they were more likely that they actually voted for Roosevelt, right? So if we wouldn't have required that you own both a car and a telephone to send out this survey, we would have actually had not a selection bias. Okay? But because they required the names to have a car registration and a telephone number associated with them, we ended up with only people in this group in our sample. We had a selection bias. Question?
Yeah, so why are we not using percent for the car and telephone?
What do you mean percent?
54% of people with a car and telephone still voted for Roosevelt. So it seems like the respondents changed their opinion.
So 54% of people voted for Landon. 46% of people voted for Roosevelt in this group. Right? So this is of the people they sent something out to. Who did you vote for?
Okay, sorry.
52% voted for Landon. 46% ended up actually voting for Roosevelt. This wasn't kind of what they responded in 1936. This was the follow-up. This was the follow-up survey. They said, who did you actually vote for?
I think he was asking, what are the parentheses numbers next to the numbers?
Oh,
54.9.
These numbers right here. I forget what I'd have to go back and look at what these, if I remember correctly from this paper, what would this have to have represented?
Would it be a difference?
So, no, this was looking at, so the percentages, so this is why I circled these. This is based off of the people that they like contacted, like after the fact when they went back out and found them. This wasn't like their initial response, right? This was like what percent of the overall group they made up. But notice here, like this 27.3, people who owned a car and telephone when they went back out and reached out to the people who had a car only or a telephone only or both, or they also found people who had neither. This was like only 27% of people were in this category, right? So if you like add up these values here, these should be 100% of all the population, right? I don't want to get too lost in the weeds of this, but like I have 4 different groups. I had neither a car or telephone, only a car or both, right? So of the 27% that had a car and telephone, 52% of them voted for Landon, 46% voted for Roosevelt, right? These are something about like the overall percentages relative to the entire sample they had, right? So we're kind of focusing on this first column in each one of these categories, okay? So this tells us that we had an over selection of a group where people actually did tend to vote for Landon. If I had only relied on just them having a telephone or just a car, this would have been my sample and I would have had more accurate data, right? Because I wouldn't have been just over selecting from this group. Now my sample would have included everyone in these first three groups. Now, if I had no requirement at all, and I had just completely sent this out randomly, I would have had people from every single group, in which case I would have also included the neither, in which case the neither was significantly higher. Okay. So this is just kind of going to show like I have, right, no matter, my selection bias, I was excluding all of the groups that actually had a higher percent vote for Roosevelt. I was only including in my sample the group that a higher percent had voted for Landon. Right? Now, in terms of the non-response bias, this is the one where I said there's no reason to believe, I don't know, were people in a car and telephone any more likely to send this survey back? I wouldn't have thought so, but I forget what they say in the paper. They go through, we're not trying to like evaluate their academic career here, but they go through some thought process of like, if I own a car and telephone, I was likely in a large city and I was wealthy. And so maybe I'm working in a field where I'm less likely to have time to respond to a survey. Whereas if I'm like, or in a rural place, maybe I have more. So they can't try to come up with some explanation. But what's interesting is when they went back and looked at these different categories, people who owned both a car and a telephone, car only, telephone only, or neither, when they actually looked to see, did you respond to this survey? For whatever reason, every single group, people that got this survey, if they were gonna vote for Landon, were just more likely to send that survey back, right? Once again, they go through something about civic duty and I don't know why that might be the case, but we wouldn't have known this ahead. Like I said, ahead of time, I would have just assumed we wouldn't have had a non-response bias here. Why would someone that only owns a car or only owns a telephone be any more or less likely to send a survey back just because they're going to vote for one candidate? And I think maybe at the time, maybe if like one candidate was more popular, then maybe I just didn't feel like I had to send the survey back. There was some explanation there as well. But all we're focused on is what the data shows us here is every single group was returning this survey back at higher rates if they actually ended up voting for Landon. So nothing we could have done, even if we would have sent this survey out to every single group and avoided the selection bias, we still would have had this non-response bias. Okay, so this is going to exist in our data sets when we think about looking at survey data, or even if we're gathering data. If there's some data that's harder to gather, we might have, it's not really a non-response bias because it's not to a survey, but we might have like a non-collection bias, right? That for certain groups, maybe it was just harder to gather data on. Or essentially, this missing data is going to cause us to have a sample that's going to be biased. That's the end result, right? So there's no like questions I'll necessarily ask you kind of like in depth about this. This is kind of a fun little example like where it shows sometimes because of the procedure we used, we can create a selection bias. But sometimes there's nothing we can do about the fact that there's a non-response bias, right? It didn't matter which group we would have sent this to, they all had this non-response bias built. So we didn't have everyone, right? We didn't get 10 million surveys back. We had missing data. So how is that going to influence our results? So if I have random missing data, just intuitively, what do you think this is going to do to our results? So if I have a population and I want to estimate the relationship between two variables, and for just whatever reason, I'm randomly missing 20% of that population, right? If it's completely random, a coefficient estimate should stay the same, right? It's not measurement error, right? We've got not random measurement error now, we just have randomly missing data. So essentially, what is it like? If it's completely random, it's almost like I went up from having a data set of 1,000 people to having a data set of 800. So I would just be like missing different points on the scatter plot. But in terms of like the direction of that linear line of best fit, just because I'm missing some of those points, that line should still stay in the exact same location. Because I have a lower sample size, even though my line of best fit, which that slope is our coefficient, even though the coefficients stay the same, if I have a smaller sample size, what's going to happen? So this is going back to where we're almost like doing things that are kind of easier. We're going back to like stuff, not week one, but quite a ways back. If I'm thinking about this test statistic, it's my coefficient estimate divided by my standard error, which we know here is going to be some function of my sample size, right? I know we did stuff like this on the first exam and kind of going back to earlier material. So if it's completely random, and just to kind of give you an idea, so let's say this was like the actual population data, and I'm just randomly missing some. So maybe I only have these observations. I'm still going to get that kind of same line of best fit, right? So the slope of that line of best fit between that X and Y variable, that coefficient estimate is going to stay the same, even though I have random missing data. But if I have missing data, my sample size would be lower, which is going to do what to my standard error? Well, if it's in the denominator, lower value means my standard error would be higher. This is in the denominator for my test statistic. My test statistic would then be lower. If I have a lower test statistic, my p-value goes, get more area to the right, it would go up, and I become less likely to reject the null. So when I have missing data, it's not a huge concern if it's random. It's not a huge concern in that, kind of like with my measurement error, I'm going to end up, I'm going to end up with the same coefficient estimate on average, but I'm going to have less statistical significance now. All right, so with missing data, it's really synonymous with thinking about it as though I simply have a smaller sample size. Right? Any questions on this idea? I know I kind of mentioned this graph before I drew it. And it's kind of hard to see, right? And if you don't have colors, it's probably hard to reproduce. But it's essentially like we just have slightly fewer of these points when the data is just completely randomly missing. Now, what if, so we'll go back here and then I'll come back and draw something for you. So what happens instead if my missing observations are correlated with X, right? So what if I'm more likely to be missing values when that X variable is really high? So I'll draw an extreme case where we can think about this, but what's going to end up in being true in that case, is we would still kind of end up with having an unbiased estimator, right? It's just now we're going to have a smaller sample size. We would still have kind of lower statistical significance, right? So less precise because we have a smaller, it's the same idea, right? So what this would look like is if it's correlated with X, the reason why we're missing data, we'll do the same thought experiment. Here's X, here's Y, here's all of the population data. So if I run this regression, my line of best fit would look something like this, right? Now let's think about what if I'm missing data and it's correlated with values of X. So in my thought experiment, what if for really high values of X, for some reason, we're just missing that data? This could exist in like, I'm doing a project right now where I'm looking at the incentive effect of 1-on-1 free throws. And when you look at the data for players that play a lot, there's a ton of data out there for them, but for players who are riding the bench, they just don't show up in the data set. So the missing values are correlated with really low values of X. It would just be the kind of exact opposite of an example. But why doesn't that really matter if I have this kind of linear effect? Because then what would my data set look like? So let's say I never see anyone above this value of X. The missing data is very correlated with X. I don't see anyone past this point. Well, I would still have all the observations in this range. Whereas if I estimate a line of best fit, what would I still end up with? Same line of best fit, right? It's just that it's going to be from a smaller sample. So once again, unbiased estimator, but I'm going to have decreased statistical significance, right? So whether or not the data is randomly missing or whether or not it's missing in correlated values of X, it shouldn't matter for that relationship that I'm estimating. One caveat, which I will add in and not try to confuse anybody in a little bit, but we'll hold off on that first, okay? Any questions on this idea? Once again, I know this is harder to reproduce without colors, but tablets and things like that are getting easier and easier to do that. So what's the third scenario that we have, right? And I should be kind of careful here. even though it is unbiased, what's one issue we could end up with if this is the case? We might now have some external validity because technically our results are only for people who had low values of X and not for high, right? And if we had anything that wasn't a linear relationship, which is what I'll draw for in a second, then maybe our external validity will be challenged, right? So I'll show you an example of that in a second, but I want to go through kind of the third example first. So we'll kind of return to that. So what if the missing observations are correlated with the values of Y? Well, there we actually have threats to internal validity. We might actually not be getting the correct estimate because the expected value of our error, right, is now going to be correlated. No, the expected value, sorry, I just didn't say correlated. The expected value of our error term for different values of X might not be 0 now, right? Because in my simple thought experiment, maybe now, what if, here's all my observations. Here's the population data. Okay. Well, now if I have this line of best fit for the entire population data, I'm okay. But if the missing values are correlated with Y, now if I don't see anything above this Y value, now the expected value of my error terms, right? Or I would have kind of had value that might be consistent. Now for different values up here, I'm censoring off all these observations. So now I'm forcing like my predictions to only have negative errors for these high values of X, right? So when my missing data is correlated with Y, I'm now changing that the expected value of my error term here, it can only ever be negative. So the expected value can't be 0, those values of X, right? So when we have when we have missing data that is not random, but correlated with the Y values, there I'm violating that same assumption that our measurement errors violated, right? The expected value of this epsilon error term in our regression, given different values of X, might no longer be 0. So we kind of think about what's kind of a similar idea here. You know, maybe if the missing values were only for individuals who were more likely to vote Democrat, well, then when I ran the regression without those, I was kind of, you know, whether or not my dependent variable there was whether or not they voted for Landon. If the fact that they didn't send the survey back was in any way correlated with not they kind of actually vote for Landon, correlated with that Y value, I might now see a different estimate, right? I might have a bias estimate, or I had selection bias essentially. So that selection bias is just a different way of thinking about I had missing values, and it was because I over selected a certain group. But the values I was missing were dependent on Y value. Right? It's really just a different way of thinking or saying that we had a selection bias, right? That the missing data was correlated with those Y values. So this is our big concern, right? I'll kind of take a look at this and state it here just to kind of prove ourselves. This was some data. Where are we at in time? So I did want to go through one thing here. That could look a little bit different. I probably wouldn't push you guys this far. So it's just, this is one of more of those, if you're interested things, right? So I said that it doesn't matter if the missing data is correlated with X. It only mattered if it was correlated with Y, right? And that violated that assumption that the expected value of the error given X was equal to 0. But what if, let me use this correctly, there we go. If I'm trying to look at different models, right? So in my assumption, I said it didn't matter if it was a linear relationship, that I was missing values above us, right? If it was correlated with X, so it didn't matter. Now, what if instead I'm trying to estimate a relationship that is nonlinear? So what I had in the slides there, and as far as I would expect you guys to answer, is only how would that missing data that's correlated with X impact my results from a simple linear regression, right? And we said it wouldn't impact the size of that coefficient. It would still be unbiased, right? Now we said the statistical significance would be lower because we had a smaller sample size, but it didn't impact the size, right, of that estimate. If we had a nonlinear relationship, when I go to estimate this relationship, if I use the full sample, I guess I should keep this in the same color, sorry. It would look something like this. So here, what would I expect about the squared term of this x variable? It looks like this is nonlinear. So if I included the squared term, I would expect that it's not a linear relationship. So if I run, so let's say this is the regression I run, right? Well, first of all, this is increasing, but at an increasing rate. So I would expect that sign to probably be positive. But I would also expect it to be, if this isn't a linear relationship, the square term will be statistically significant. Right? The only reason that that squared term becomes statistically significant is if we have a relationship that isn't linear, which maybe I should have drawn this more extreme, but right, we have a non-linear relationship here. If I had an example here where I have missing data, right? Is there any questions on this? Does this make sense? This is a little bit of a review as well, right? If I'm looking at this and I'm thinking about the squared term, once again, we're just picking up the relationship between x and y. It is y is increasing as x goes up, but at an increasing rate, right? The fact that this is not a nice linear relationship tells us that that squared term will be statistically significant. Now here, if I'm missing values that are correlated with x, so now once again, the thought experiment is, I don't see anything here in my data set now. The missing values are correlated with x. Before, when it was linear, it didn't matter. But now if I estimate this relationship, what does it look like? It actually looks like it's linear. So when I'm trying to pick up linearity, like if it's a linear or non-linear relationship, if I have missing values that are correlated with x, it might actually, if it was a simple linear regression, doesn't matter. If I might have something that's non-linear, it could now lead to me thinking that the square terms coefficient in this case would be what?
Significant.
Less significant. In fact, it looks linear, so it's likely that that square terms coefficient would be statistically insignificant, right? So if we're talking about nonlinear relationships, there the missing data becomes a bigger issue. An issue that, like I said, I won't expect you to we won't dive into in terms of questions on the quiz or the exam for this class. But to kind of relate it to what we've talked about, do a little bit of a review, and then think about kind of what the next level would be. Missing data correlated with x only doesn't matter if we have linear relationships. If we have nonlinear relationships, now it might matter, right? Now it might lead me to identify the incorrect model. Does this, any questions on this? Hopefully this is, we're starting to see kind of how, I know these topics seem like very separate, but hopefully we're starting to kind of see like we can kind of connect a lot of them. Where are we at in time? Okay. So I've got some stuff that we'll do in Stata here, which I think is why, yeah, I left out like a slide here. This is for some of what I was drawing, but we got some Stata work we'll do as well. I don't know if we'll really dive too much into this simultaneous causality. We'll touch back on this when we talk about instrumental variables later on. That'll be the last kind of week of new material that we cover. So for today, what we'll kind of jump to right now, let's see. Before you open this, I forgot before I hit publish. Let me set this due date here real quick. What time is it? 15. So we'll do, make sure we leave it open for a while. Shouldn't take us 10 minutes to get through this, I don't think. But just in case we have Wi-Fi issues, we'll have the next 10 minutes to kind of submit this. So go to this in-class quiz 10, should be under the homepage. Let's just double check before I tell you that. I believe I added it down here, right, under week 12. We're then going to kind of think about, this is type of question you might see on the quiz, or you might see on the final. So here, we're thinking about which of the following would cause an unknown bias. Yeah.
What's the code?
Oh, sorry. 11.17. So 11.17 should be the code. verify that with me? Yeah. So which of these would cause an unknown bias in my coefficient estimate, right? Or my slope coefficient? So which of these did we say, first of all, if we just think about which of these could we actually make a statement about the bias for? We had two types of measurement error, whether it's in the independent or dependent variable. We had classical. I said you could think about this as completely random, or we had non-classical. It depended on values of X or Y. So if I have classical random measurement error, this is not the most technical way of saying it, but usually that is a good thing, in the sense that we can make a statement about it. So when we're thinking about what has an unknown bias, it's not going to be classical measurement error. If we have classical measurement error in the dependent variable, Y, we said today, and we saw with the GDP, what did that do to our estimate? Nothing. Didn't even change the statistical significance, right? So classical measurement in that dependent, we know the bias. The bias will be 0, right? Now, when it came to classical measurement error in our independent X variable, that was the one where we had this function. It was the function of the variance of the measurement error, or sorry, the variance in the variable over the variance of the variable plus the variance of the measurement error. So it was this kind of like scaling factor. When I take a number, I divide it by that same number plus something. I know that that fraction will always be less than 1. We said when we had classical measurement error in our independent X variable, that always did what to our estimate? Caused our estimate to be 2. I multiply something by a fraction that's less than 1, it's going to be smaller, right? So we had attenuation bias towards the value of 0. So classical measurement error in our independent variable caused not an unknown bias. We know the bias will be that it pushes it down closer to 0, right? It won't push it past 0, it just gets it closer to 0. And the actual size of the bias could be computed because we said that scaling factor that tells us what that bias was just the variance of the variable that had the measurement error divided by the variance of the variable with the measurement error plus the variance of the actual measurement error. That was something we kind of looked at last class, that actual kind of function. So classical measurement error can't be the answer here. Now, if we have completely random missing data, what did we say was true? If I'm just thinking about the bias, that's telling me the value that I'm seeing for that coefficient estimate. Nothing about the statistical significance, right? So when I had completely random missing data, what did that do to my coefficient estimate? Didn't change it at all. But what's the bias if I have completely random missing data? Bias would be equal to 0, right? I'm getting the correct estimate, right? I just have fewer observations. So if there was another question where I said, what happens to the statistical significance if we have random missing data? Well, there we said that statistical significance would go down or be less statistically significant. So the only option we're really left with there, the one that has unknown bias, is when we have non-classical measurement error and it's in our X variable, right? We even said if we have non-classical measurement error, right, and it's in our dependent variable, right? If it's if it's correlated with the values for Y, or the values for Y, we said, or the values for X, sorry. We said it's really just like we're getting a different portion. So that was the one I drew out where that was the second one where we then kind of extended it to say if it was nonlinear. Or it's just that, there we go. All right. So if we had non-classical measurement error in the independent variable, right? Oh no, I'm doing missing data. Did I draw that one out for us today? Yes, right? When we had non-classical measurement error and it depended on kind of values of Y, right? It was, no, this is my missing data again. Where the hell did I put that? We did it at one point.
On the bottom,
Huh?
like you shift into the bottom.
Oh, right. So this was still missing here. We'll look at this. If we had non-classical measurement error, we can kind of think about, well, we didn't have a picture for it now that I'm saying this. That was the example I gave you of what? When we had drug use and kind of whether or not they were a police officer, we said if it was non-classical, that meant that for different values, we were gonna get different sizes of the measurement error. There, what assumption did that violate? Well, now the expected value of our error term for different values of X was going to be something other than 0. We will have a bias. And we didn't know whether or not the bias was going to be positive or negative. So the only kind of answer we have here that's going to cause an unknown bias should be when we have non-classical measurement error in that independent variable, right? The other three, we can say what the bias is. 2 of the cases, the bias was 0, random missing data, classical measurement error in the dependent variable. And then classical measurement error in the independent, it's not unknown. We know that it's going to be attenuating it towards 0, and we can actually tell what the size of that bias is using that kind of fraction. Okay. So the only one that's unknown is that non-classical measurement error when it's in our independent variable. Okay. So that's kind of talking through some of this a little bit more. The other question everybody should get correct. I have it kind of, so just as long as you work something, you'll get the credit for the answering the question. So let me just make sure where we're at on time so we get this submitted. Yeah, we got another 3 minutes. So basically, which would you want to see more work on, or what have you found most confusing over the past couple of weeks, right? So we have the stuff that we were talking about today, kind of bias existing from measurement error or missing values, right? Model comparisons, if we're thinking about which model do I choose, log versus a quadratic versus a cube versus linear, kind of those model comparisons, was that something that you found most confusing? Or coefficient interpretations and marginal effects from either nonlinear models, right? So quadratics or log models, or coefficient interpretation and marginal effects when we had interaction terms, right? So look at these results. I kind of might dictate what I do kind of moving forward in the next coming weeks, because I can sprinkle in some review based off some of the topics we're going to talk about. And I want to kind of focus what people are wanting to see a little bit more work on. Okay. Questions on this? Okay, so make sure you're getting that submitted here. We've got another 2 minutes, so make sure you're hitting submit. Pretty good. We're able to get into the quiz okay. So if we go back to that do file, right? I've got some kind of examples set up here where we can actually look at some of this missing data and once again prove this to ourselves with data. So I've got this free data set, which is this birth weight. So that BQs, I think I'm probably going to have to, okay, I already had it installed. To access this is this free data set that exists in Stata behind the scenes, right? So I'm going to create this completely random number. I think it defaults between 0 and 1. Let me see. I can actually see what it does because I didn't set it. It must default to. So I created this random number somewhere between, yeah, it looks like 0 and 1. Okay. So I'm going to sort it. And then what this does is it basically just selects the first 1,000 observations. So I've created this random number, and I'm basically just choosing 1,000 of those random observations, right? Just kind of picking them out of this data set. I'm then going to think about, okay, I'm going to replace family income with family income miss. So this will be like the data set I see that has a bunch of these missing values. Okay, so if I go ahead, run this code, when I look at the data set, I'll have this random number, right? I was selecting the first 1,000 observations. After the first 1,000, they're all missing, right? So I'm kind of randomly missing what? There was a total of about 1,400 observations. I've only got 1,000 of them. I'm randomly missing 400. Okay? So if I run the regression that uses the actual data with family income that wasn't missing, I then run that regression where I try to predict birth weight with family income where I have this random missing, like just randomly missing data. If it's completely random, what should be true about the coefficient estimate that I see between these two? Completely random, it would be classical. Okay. So if I have, sorry, classical. I shouldn't say it that way. Okay, so if I have completely randomly missing data, right? All I have was basically that scatter plot, and I have fewer of the points. So we said if I try to estimate a line of best fit, I'm still going to end up with that exact same line of best fit. So the size of my coefficient shouldn't change at all. But what is going to be impacted? Well, I no longer have all 1,400 observations. I only have a random 1,000. So my statistical significance should be lower, right? A less statistical significance, right? Or my p-value would be higher. So I can actually run this regression, right? The one with the actual data, I get 0.007, test statistic of 4.08. So it's a little bit off here, right? Now that's going to be because if it's completely random, what would I really need to do? I need to randomly generate those numbers, kind of like we did last class, like 1,000 different times, and then look at the average coefficient, right? But we can see here, it's pretty close, right? In fact, I think down here, this is basically what I'm doing to kind of prove this to us. So here's where I would not expect you to do something like this on the problem set, right? But if I created this program that randomly created this number and randomly selected 1,000 observations, and I did it, 100 times here. Now, when I run that regression and look at, okay, compared to the original value, well, it's taking some time here. See if we get 70, 80, 90. So for the actual population data, our estimate was 0.0074. Okay. If I randomly kind of have these missing values and I do this 100 different times, on average, the coefficient estimate I see is 0.0075. So it's still a little bit off. Theoretically, I would need to be able to do this not 100 times, but like an infinite number of times. But essentially, our coefficient estimate isn't impacted by this random missing data. Now, if I think about what's going to happen, we go up here, and I could do the same kind of thing with running this 100 different times. But if we just go back to where I ran it once for just one set of random numbers, what happened to my statistical significance? Now here I can actually see the p-value just barely went up. So this is where when I'm asking you these questions on a problem set, or I'm asking you like on a quiz or exam, if I ask you what happens to the statistical significance, it still might be statistically significant. Well, what happened? What direction did the statistical significance change? It went more or less statistically significant, less, right? So I would have a less statistically significant result, even though it's still statistically significant at the 99% level. Okay? Now, if I didn't see these p-values, how would I know that it's less statistically significant? Because my test statistic is lower. So this is where even if I still could see p-values where it looks like it's still 0, if the test statistic went from 10 to 7, p-value in both cases is 0, but for that test statistic of 7, the p-value is going to now be larger, right? So we would still know that the statistical significance still went down, okay? And this would be true if like we're comparing, log linear versus log results, and we're kind of seeing which one of those coefficients is statistically more significant. We might not be able to see it out to the third decimal looking at the p-value. Almost always we can see it to the second decimal in the test statistic. I then kind of had an example here. So let's say I've got completely random missing data, it's not completely random anymore. I'm now missing all the family income values below 30,000. So it's almost like now, instead of my example earlier, I said we're missing the high values of X. Now we're missing the low values. So it's not completely random. It's correlated with what that X value is. So if we go ahead and do this, right? What I should still end up seeing is that coefficient estimate. Oh, what didn't I do there? Family income. Name the wrong thing. Not dropping any observations, so that doesn't make it. So tab, we do some family income. It looks, because this is already in thousands, so 30,000 would actually be 30, right? So instead of 30,000 here, I'm going to drop 30 represents 30,000. If I run this regression where the missing data correlated, notice it does look like my coefficient goes up. But once again, if I ran this, right, the missing data is correlated with my X variable, it could potentially be that I now have like a very different set of the scatter plot, and I could end up with a slightly different slope coefficient, right? So what this would tell me is It only is the case that coefficient won't change if it's a truly linear relationship. So the fact that it is different here tells me that because I had a different portion of those X values, it's likely that there is some slight nonlinearities in this relationship, right? That even though I was estimating it and treating it as though it was linear, when I'm looking at family income and I'm trying to predict, I think this was birth weight, that maybe the scatter plot looks something like this. So if I estimate this as a linear relationship, it's not really appropriate, but if I do, if I'm then missing all the low family income values, what will my new estimate look like? My line of best fit, that slope could be different. So I won't try to throw too many of those types of examples at you, because then we start to get some really difficult concepts of like combining nonlinear relationships with missing values, and there's a little bit. So as far as I want you to think about is if we did have two variables and we know the relationship is linear, then having missing values that are correlated with X shouldn't matter. If we have any non-linearities, then having missing data correlated with X, there that might change the size of our coefficient. Man, is there something important going on today? Everybody's missing? Everyone's leaving early? Maybe I should do like an impromptu extra credit quiz.
Yeah.
So if I had one set up, I probably would. Maybe I'll have one ready to go if people start doing this in the future, right? So once again, we'll kind of leave it there. We could do a similar thing with Y. I might revisit this at the very beginning of class next week. But what I would say is you should have everything we've talked about today. That slide of simultaneous causality, there won't be anything on the quiz that's